Again, a recap. The result that we ended up showing last time, just remind you, there are two sets of results, one about the expectation and the other one high probability bound. So what we showed is that if you consider an empirical risk minimization, so again, to remind you guys, LNH is just 1 over n summation LHZI 1 to n. And this is 1 over n summation I from 1 to L H xi and yi. And so we minimize this over class of functions h. And we also look at this loss class, which is just the class of functions that look like this. Basically, you want something like this as h varies in h. So these are functions on z. And then if this class has VC dimension v, or nu, then the expected excess risk or excess loss of this empirical risk minimizer is bounded by 4 times this Rademacher quantity. And then this is bounded by nu log n over nu divided by n. So this behaves like root nu log n over n. Okay. And so this is a high probability. This is an bounded expectation. So the expectation is over the randomness in Z. There is another version which is high probability bound, and this allows you to state that this quantity, which is random, is bounded by this with probability which you can control. Okay, so there's this extra factor that we pay, and this comes from the bounded difference inequality. So we saw that basically the map that maps Z to the supremo of this empirical process, this map, we're going to show that this is de-bounded, and so it has bounded. The class is de-bounded, so this has bounded difference property, and then you get the concentration inequality. We control the expectation of this by the Rademacher expectation of the Rademacher complexity, and then so this is the expectation of the Rademacher bound on the expectation of the Rademacher complexity, and this is the part that comes out of the bounded difference inequality. Okay, and I mentioned that, so there's an assumption here that F contains this loss class and is symmetric, and you can remove this symmetry. And then furthermore, the VC dimension of this class is upper bounded by the VC dimension of H. So if H has a finite VC dimension, the VC dimension is nu, then this result holds for that. So today, I want to do something which is basically a technique to remove this log n, and then you get root nu over n. This is sort of optimal. Okay, then you can show that you can improve this. We may see that at some point. So in particular, for every possible estimator, or not necessarily this guy, any possible estimator you can think of, there exists a distribution such that this is lower bounded by this quantity, nu over root nu over n. In the case where the ideal risk is non-zero, if the risk is 0, you can improve this if the population risk is 0 by removing the root, so you get nu over n. So that's called the fast rate. So goes faster. But in the so-called agnostic case, where the population loss is not zero, you can't improve this. So today I'm going to try this. Later, you might see the lower bound as well. So we move this, and so you get about like root nu over n. Questions? Okay. The other point was that there is the relation between the linear algebraic dimension and the VC dimension. So if you have a vector space of functions, dimension is finite. So dimension G, and you get this subgraph, like or subgraph or sub-level sets. These are the sets that are defined like this for some G in the function class. Then the indicators of these level sets or sub-level sets will have VC dimension bounded by the dimension of the subspace. So I'm not going to repeat the proof. See some examples. The main example is this one, which is useful for us. So if you have a class of half spaces, okay, in RD, so you know the half spaces can be written like this, right? So there's this. Okay, sorry. There is this normal to the half space, and there's this sort of intercept, and to the one side of it. So we want. So how does it look like? So if I have something like this, what is this set? If I said x equal to 0, this would be b. It's normal to this. So is 0 in this set? So if b is positive, 0 is not in this set, right? So this would be this side. Right, so that's the ax plus b less than or equal to 0. So you're looking at the class all half spaces, and so this is a subgraph class associated with this sort of affine function or affine function class. So all the functions that look like basically map. So this means it's like h of x is ax plus b. Okay, and this notation ax is just the inner product, right? Sometimes we read it as like A transpose X. So this is so the dimension of this, this is a vector space of functions, right? So if I add two functions that look like this, it's again a function that looks like this. If I rescale, rescale these two. There's a vector space, and the number of parameters is d plus 1. You can convince yourself that the dimension is at most d plus 1, right? And so by this result, the VC dimension of this sublevel sets, like hyperplanes in RD, is d plus 1 at most. And then you can argue that it's actually, in fact, d plus 1. Okay, in order to do that, you have to show that basically no d plus 2 sets of points can be shattered. Okay. Good. There's another example which just to briefly mention, but we can skip. So let's say if you have circles or spheres in RD, these are the sets that look like this. You can think of them as sublevel sets of like square of this minus b squared. So if you do this, this function is like a quadratic function. And so if you think of the, let's say these polynomials, so phi of x1, x up to xt, and then the norm x squared, as you can see, this is a linear combination of these elements. So you can write a function like theta times this, where theta is in d plus 2, right? So you have actually 1 here, and then I have some coefficients here and some coefficients there. I need to like include a coefficient there because if I set it equal to 1, this is not going to be a vector space, right? So what I'm doing is that I'm assigning a coefficient to every one of them. So I have a coefficient here, a general set of coefficients there, and a coefficient there. So that would give me d plus 2 coefficients. This now is a linear vector space, right? Without adding that parameter, like there, it's not. If I add 2 things, I'll change the coefficient. So this is a linear vector space, and the level sets of this, like functions like this, contain all these guys, right? So the things that like look like this less than or equal to 0. So this is like the level sets of this is the largest subclass, and that's how you get that the VC dimension is at most d plus 2, but you can in fact show that the VC dimension is d plus 1. So this gives you the right order, but not the exact exact bound. Okay. Questions? Okay, so now let's move on to the techniques. I want to talk a little bit about the techniques that allow you to remove this log n, and they're useful. So I just it's worth mentioning, and then you can use it to. So so far we have like considered. So if you recall, you started with finite function classes, okay, and so you needed uniform control over H. And so started with a finite H, and then we saw that we can use union bound to control, so uniform control of something like LNH minus LH. The population, the empirical versus the population loss over this class H. So we started with a finite H and then showed that we can control this uniformly over H by union bound, and then we went to like the VC dimension idea. And the VC dimension idea is like roughly, things are left roughly finite when restricted to a finite set of points but then these points are random, they're training points. So we couldn't exactly use this, so we went to like the Rademacher complexities of Rademacher root, if you want. And then the notion of VC dimension was for indicator function. So it's a little bit of a, I would say, restriction. Someone asked whether there's an extension of it to more general functions. And there is, but these metric entropy ideas are sort of more general. So the idea is that we can reduce any set of functions to a finite set if we allow a certain approximation error. Okay, that's the main idea. So now we're going to talk about the metric entropy ideas. This is like by far the most general entropy ideas. And so if we so we develop these, and then we show that like if the like function class has like it's a Boolean function class with finite VC dimension, then the metric entropy grows at a certain rate, which looks like how the metric entropy of the finite dimensional spaces grow. Okay, so from the metric entropy perspective, it's really clear that a VC class looks like a finite dimensional class. So this is, I'd say this is more interesting than this connection between, so this was one connection between the VC and dimension. The other one we'll see today is via the growth of metric entropy. What is metric entropy? It's a way of measuring how big a set is. And you can think of it as a quantitative measure of compactness. So what is compactness? Anyone remembers from the analysis? The set is compact in the Euclidean. All convergent sequences can, all Cauchy sequences converge. That would be like definition of completeness. Every bounded, let's say, sequence has a convergent subsequence. That's like a, yeah. So that's true. That's like a sequential definition. There's another like more abstract definition. Yes, okay, great. So every open cover of the set has a finite subcover. So if I have a set, and so in Rn, basically compactness is equivalent to being closed and bounded. So let's say if I cover these by balls, like shifting balls around, so I can always, so think of the set, I can always, so if I have a set, let's say C, subset RD, I can always cover it by the union of all the balls. You write it like this, X plus epsilon B. So this is the unit ball of L2. I rescale it by epsilon, so the radius is now epsilon, and I shift it to X, where X belongs to C. If I put a ball of radius epsilon around every point, right? So these are around every point, then this certainly covers C. Then it implies that there exists sort of a finite, there exists, let's say, C1 up to Cn, which depends on the epsilon such that C is covered by I from 1 to n, xi plus epsilon b2, let's say. It could be any b, actually, not necessarily b2, any ball or any like set would work. Right, so this saying that given any epsilon, there exists a finite number of these shifted balls that I can use to cover the set, right? That follows from the compactness. So this is a generally a cover if you like put a ball around every point, and it says there exists not C, there's like xi's. X2. So what the metric entropy idea is that it tells you how large this is for a given epsilon. Okay, so there's some n which depends on epsilon. And it tells you how big that n is for different epsilons. Subset C, such that. Okay, so for a given epsilon, the smallest n for which I can find a set of these shifted balls of radius epsilon that can cover the set is called the covering number, and the log of it is called the metric entropy. So formally, yeah, so the notation here is a little bit different. So suppose I have, okay, so if I have something like this, then this is equivalent to saying that for every x in C, there exists I such that let's say norm x minus xi is less than or equal to epsilon. Okay, so for every point, there exists something, some I, so there is one point in the cover, this is called the cover, such that x minus xi is less than epsilon. Okay, so I can approximate every point by a point in the cover. This is the way that usually people define it. So an epsilon cover, an epsilon net of a set T with respect to some metric rho is a set like this. It's better to call it like T1 up to Tn. Or let's say theta is fine. So there is some set of thetas, 1 up to n, such that for every t, there exists a theta I such that the distance is less than epsilon. So the epsilon covering number, which is a function of epsilon and also depends on the set T and the metric rho, is the cardinality of the smallest epsilon cover, or epsilon net. Okay. And the log of it is called the metric entropy. Okay, makes sense. So this is another, I guess, similar idea. So if I have the metric is in norm vector spaces, usually you take the norm as the difference, the norm of the difference is the metric. Let's say this P is the unit ball. If I set balls already epsilon centered at these points, and if this is an epsilon cover, or this is an epsilon covering or epsilon cover, if and only if T can be T is included in the union of these balls. Okay, these two are equivalent. Here's a picture. So I put like if theta 1 up to theta n is a cover, if I put balls of radius epsilon, if it's an epsilon cover, it's just the cover is the set. Right? Every point here is in at least one of these balls. Okay, so this is a notion of approximation basically. Here, right? Okay, there is another notion which is the idea of packing. These go hand in hand. So if an epsilon packing with respect to T on a set T with respect to a metric rho is a set of points such that for every pair of distinct points, the distance is at least epsilon. Okay, so they're sometimes called, this set is called an epsilon separated. Set. So you can see it becomes harder to add more points. And so the maximum number, the cardinality of the maximum epsilon packing or epsilon separated set is called the packing, epsilon packing number. Okay. So it's the largest. So this is an example. So I've chosen these. M is the number, and basically they don't touch. If I put a ball of radius epsilon around every point, or actually epsilon over 2, sorry. If I put a ball of radius epsilon over 2, these balls shouldn't touch because if they touch, then it means that the distance of the pair is less than. Okay. Okay, so now there is the lemma. There's a relation. Oftentimes you can sort of control one in terms of the other. So the metric, the covering number, epsilon covering number is sandwiched between the packing, like epsilon packing numbers from above and below. Below is like 2 epsilon. So can you maybe argue these inequalities? So why this is true? So this is saying if I this is maximal packing. So if the maximal packing is m, so I've packed the set with m points, and I can add one more point. That's epsilon separated. then basically the hint is this. Then that maximal packing should be a covering of a suitable radius. Is this a covering? So if I like have a packing, like this is a epsilon packing, let's say it's maximal. So if I have balls of radius epsilon over 2, they're not going to touch. How about if I put a ball of radius epsilon? Is it going to cover set? Suppose I put a ball of radius epsilon around every point, right? And there is a point here that's not covered, right? Then what does it mean? It's not maximal packing because this is outside the balls of radius epsilon around every point. So if I add this to the packing, it's going to be at least epsilon apart from everything else. So maximal packing has to be automatically an epsilon covering. So if M is the cardinality of the maximum packing, this is at least a cover. So the best cover is going to be less than. So that gives you this. How about the other one? How can you argue the other one? This is saying that if I have a cover, but this is the minimum. So it's saying that the maximum covering is, the maximum packing is less than the minimum covering. Right, so if you have, so every, how can we argue this? Can we argue it? So let's say this is epsilon, this is epsilon over 2. Right. This would be this idea that if I have like a pick a maximal packing, right? Epsilon packing, right? Then it's not an epsilon over 2 covering, right? But why there is no other possible yeah. Any maximal 2 epsilon packing is not right, but there could be like some other yeah, okay, it's a little tricky. I'll let you admittedly figure it out. I'm not sure, to be honest. It's related to this idea, but to write it down properly will be assigned as a homework problem. But this side is sort of clear. We're going to use this. So let us move on. What I want to do is maybe talk a little bit about this. So if you have 2 norms with respect to unit balls and the So this is the unit ball of this norm, and then the unit ball of the prime norm is defined similarly. Then you could write these volume ratio estimates. So the covering number of the ball of one norm in the other norm is bounded by the packing number. This is the inequality that we showed. And the packing number is bounded by this. The covering number is bounded by, bounded below by that. So this sort of gives you a nice estimate. So for example, if I do this for the balls in Euclidean space, so let's say I'm going to use the same ball. So it could be a Euclidean ball, or it could be any other ball in RD. I take B prime to be the same. So I'm covering, for example, I'm covering the circle in circles, okay, or covering the cube in cubes. What happens is that this volume here would be volume of 2 epsilon B plus B, which is just going to be volume of 1 plus 2 epsilon B. And then this comes out because scaling sort of scales by, if I scale a ball, the volume just, it's easy to argue that the volume should be scaled by the factor to the power D of volume of B. So the volume of B cancels with this volume, and so you get this upper estimate. And similarly for the one, this is going to go away, you get this. And so if you focus, usually you care about the cases where epsilon is small. So if epsilon is less than or equal to 1, I can bound this by 2 over epsilon. So I get, by 1 over epsilon, so I get 3 over epsilon. So you can see the covering number of a d-dimensional ball in its own metric is like exponential in D, but has this form like constant divided by epsilon to the D. That's the point. It's good to remember this. The proof is simple. So this, let's say, at least prove this upper bound, which we're going to show for the BC dimension. Suppose I have an epsilon covering of B in actually, maybe we're going to show both. So an epsilon covering of B in these guys, then B is included in the union of these balls. And so I can use the union bound. So volume is a measure. So volume of B is going to be less than n times the volume of these. So volume of B would be less than summation I or j from 1 to n. Volume of theta j plus epsilon B. And this is just going to be volume of epsilon B, because volume is shift invariant, and this is going to be epsilon to the D volume of a B prime. B prime, and then there are n of them. They're all the same, so you get n epsilon D over volume of B prime. So you get a lower bound. So you get n is bigger than or equal to volume. So you pick a covering and ensure that the covering has to be bigger than volume of B prime. So for every covering, the number is lower bounded by this. So the minimum cover has to also satisfy this. So this gives you the lower bound. For the upper bound, you're going to do a packing. Okay, so you're going to construct a maximal packing and then show so that theta 1 up to theta n be a maximal epsilon packing. By maximality, it should be also an epsilon covering that we saw. And then the balls, if I put a ball radius epsilon over 2 around every point, these are going to be disjoint. Again, we saw that. And they're contained in, so if you look at the situation, so if I put a ball of radius epsilon over 2 they're separated. But if I put a ball of radius epsilon, that would cover the set, right? And actually, I don't need this. So, okay, what I need is something like, there could be like some part of it could be outside, right? So if the center has to be inside, but some part of the ball is outside. But it's like half of it can be outside because of the center. So if you think a little bit about this, it's going to be contained if I like increase this by adding basically. So this is B, this is B plus epsilon over 2 times B prime. So this is the Minkowski sum. So this is the set of all points that can be written as a point in B plus epsilon over 2, a point in B prime. So these balls are contained in that. And do I actually use this when covering? I'm not sure if I'm using this actually. But in any case, so the volume, so I know that the union of theta j plus epsilon over 2 B prime, j from 1 to m, this is contained in B plus epsilon over B prime. Then I take the volume of both sides, so I get volume of this guy is less than volume of B plus epsilon over 2 B prime. These are disjoint, so this volume just separates, it's equal to summation of the volume of the individual ones. And so I get volume of basically theta j plus epsilon over 2 B prime. This is less than or equal to, I'm going to factor out, should I factor out? Yeah, let's factor out epsilon over 2 to the d, I get the volume 2 over epsilon b plus b prime. And then this side is okay. So I get summation over j from 1 to. So these are going to be just each one would be volume of epsilon over 2 to the d, volume b prime, and this would be m, right? So I get something like that, epsilon over 2 d, volume 2 epsilon b plus b prime, and then these cancel out, right? So this cancel out, and I get that m is less than volume. Divided by 1. Okay, that's what we wanted to show. So m is bounded by this. I don't think I use, sorry, I don't think I use this fact. Do you use this fact? Yeah. What is true? The maximum. Why? Yeah. So let's say, what is the set that we are trying to do? There's like the reference set you're going to pack and cover. What is this one? It's like unit. Sorry. Okay, so I have. Let's say this is 1. And then I have another one, which is 1 plus delta. Okay. How we can make. So we're talking about the same set though. So you have to like pick a set. I am saying, let's say I have an epsilon packing of this. Oh, you're using this for packing. So you're saying this is a one packing, right? But it's not a one covering. So let's go back to this. That's an interesting point. I think, so how about if I have two? If I have two of them, would that work? Like there are 2 points in the packing. So let's go back to this argument. The way that the argument works is that I have the packing, right? So they're going to be epsilon 2 over 2 apart. So let's say they're going to be, if epsilon is 1, they're going to be 1/2. Sorry, if I have a ball of radius 1/2, they're not going to touch. But if I have a ball of radius 1, we think. So what is wrong with this argument that I'm having? So if I have the, so this is an epsilon packing. Right? If I put a ball of radius epsilon over 2, they're not going to touch. So now I suppose this is maximal. I put a ball of radius epsilon. And then I can find a point that's not in either one of them. The thing is that I can then add. Right. So okay. So that's the thing. Sort of in this case, if it's in like a one packing, this should be like the ball should be a radius 1/2. That's the kind of right. So you're thinking it's just because there's no other point there. It's hard to imagine, but you have to think of this as like a ball of radius 1/2 around it, right? And then I can find like if there's a tiny bit here, I can just put another one. Right. Yeah. Interesting. Okay. Any other questions? So this proof is very simple. Just go through for yourself. The idea is that for an upper bound on the metric entropy, it's interesting to use the packing. Okay, so you look at the maximal packing, and then you bound this, and then it gives you an upper bound on the metric entropy. This is like a general technique you can use. Okay, so if you want to control the metric entropy, you can try to come up with packing which is of maximal size. Okay, so the conclusion is what I have there. And so is this clear? Okay, so now let's move on. I want to show something like this. Let F be a class of Boolean. So online people, are you okay? I suppose, okay. So if I have a set of class of Boolean functions in a probability space, I'm using the notation that I used before. So these are on set Z. We're thinking of them as, for example, those pairs of x, y's, but it's general. It doesn't have to be like that. And then the P is a probability measure, basically. This is the sigma field. It just doesn't matter. And then VC dimension is new. Then for any epsilon 0 to 1, the covering number of this Boolean function class in the L2P is like this. So 2 to the epsilon to the CV. Okay, if you compare with the estimate that we had, so for ball, let's say L2 ball if you want, in the L2 norm, that was like 3 over epsilon to the D. So you can see like up to a constant, this nu plays the role of d. Okay, but that's a nice way of saying that BC classes look like having dimension, like a constant times nu, although it's a combinatorial dimension. It's not like a linear algebraic dimension, but the metric entropy picks it up in the same fashion. So the growth, like the classes, and so L2P here is. So we're looking at putting the norm here, right? This is like if you want, you can write the norm L2P to be precise to match. So the norm is integral f squared x dx or dpx or z in this case. So we can define this z dp, right? And then later, I mean, I'm going to use the empirical norm associated with this empirical measure that we define, where PZ is, I have a bunch of endpoints. Just given endpoints from the space, I have an empirical measure. I can define the L2 of this measure, and that would be the integral of this with respect to that measure, like integral f squared z d p capital Z, let's say z, which is just 1 over n summation f squared zi, I from 1 to n. This is a very important sort of quantity. It's like usually we work with empirical norm with respect to some, like, let's say, training data. And the idea is that this norm is going to approximate that norm. If you, like, randomly, if you IID draws from P, the Z1 up to Zn, or IID draws from P, this norm is going to get very close to this uniformly over a big class of functions. Okay, so they have these norms in mind. So this result is about covering in the population norm, but then we reduce it to something like this. So let's try to do that. So this is from the HTTP book. This is a very nice probabilistic argument. So we first show that if I restrict the class to an endpoint set, so there exists an endpoint set Z, I'm viewing Z both as a vector and as a set. Okay, so in this sort of result, I'm thinking of this as a subset of the general set Z. There's an endpoint set such that FOZ, this is the restriction of F to this class, has the same covering capability as F. So it's like doesn't change the covering number that much. So the formal statement is like this. Let's F be a class of n Boolean functions that are epsilon separated in L2P, right? They're packing, epsilon packing. Then there is a number n less than C epsilon to the negative 4 log n. N is the number of Boolean functions in the class. And an endpoint set, so n is here. So it's like, this is the maximum that I need to choose. There is this endpoint set with n bounded like that, such that f is epsilon over 2 separated in this L2P empirical norm. Okay, so what this is saying is so what this is saying is that so this epsilon separated means f minus g L2P is bigger than epsilon. If f and g are in F and F is not equal to g, this one means f minus g L2PZ is bigger than epsilon. Again, if f and g are in F and F is not equal to g. Yeah, epsilon over 2 separated, sorry. So if I have an epsilon separated set, then I can have an epsilon over 2 separated set in that. And this is rewriting it is just if I square it, it's like 1 over n summation f minus g squared zi I from 1 to n is bigger than epsilon over 4. And this is just saying integral f minus g squared z dp z is bigger than epsilon squared. Okay. Is the statement sort of clear? It's a little bit of a complicated statement, but what this is saying is basically once I restrict myself to this, these functions are still separated enough. Okay, because if I restrict myself to a subset of points, it could be that these functions are no longer separated enough. They could even coincide. But this is saying that if this n is not too big, right, then actually if it's big, it's better, right? So if the bigger it is, the better, right? This is saying that it can be small. Like if I just do 1 point, they're not necessarily going to be epsilon or separated. If I add 2 points, then there's a chance that they're more separated. And then if I add more, they're saying that there's at most this much. So I can have something which is less than this. So, and being bigger is easier. So this is a nice thing to say. Like I just need log in the log and log cardinality of the set. The number of points log cardinality of the set. Okay, so let's try to prove this and then see how this works. To choose this is proof by the probabilistic method. Probabilistic. So anyone knows what probabilistic method is? Proof by. So, you know, online people. So the idea is that I want to show there exists an endpoint set with good properties. I'm going to pick a random set with some distribution and then show that the property that I want holds with probability bigger than 0. Okay, then there should be at least 1, right? So this is a very powerful technique using combinatorial arguments. So what we do is actually choose the set Z random by choosing the Z1 up to Zn IID from P. Just draw IID n endpoints from P, set Z to be this, and I also have this generic Z here. Then fix a distinct pair f and g in F, let H be F minus G squared. Then if you look at these statements here, you can see this squared, sort of the square of the empirical norm is just 1 over ni from 1 to n h divided to the zi. So this is like an average. And then the L2p is just the expectation of hz, right? This is, you can think of this as the expectation of f z minus g z squared, assuming that z is distributed like p. Right, so this is h z squared. So one is the empirical average, the other is the population average. The next step is to show that, so I want to show that this quantity is close to this, okay? And you can see this, like the concentration equality, empirical average close to the population average. I'm going to show that, so I want to control the deviation, which I can write like this, I from 1 to n minus expectation of h z. That's the deviation of the two norms. Each individual quantity here is sub-Gaussian. And so there is this sub-Gaussian calculus that I can do This is from the HTTP book. So there is a sub-Gaussian norm. Have you guys seen the sub-Gaussian? If you have seen like 200C, you've seen it, but it's just similar to the sub-Gaussian standard. So it's a norm on the space of random variables, such that if this is finite, then the random variable is sub-Gaussian. And it's related to that sigma that we had. So there is this result that up to a constant, I can remove the expectation. So this is called the centering lemma in the HTTP book. So the psi2 norm is up to constant, the universal constant. We have this inequality for any random variable x minus its expectation. The psi2 norm is bounded by the psi2 norm of the uncentered version. And then the psi2 norm of a random variable is bounded by the L infinity norm, which is the L infinity of the random variable, which for bounded random variables, this is basically finite. This is like the essential supremum. So this is because h is, so f and g are Boolean, this is a bounded random variable. So this is like bounded by 1. This is all to constants. So it's just roughly saying that this is a bounded random variable. Okay. And so bounded random variable is sub-Gaussian, and the sub-Gaussian standard is 1. So I can write the Haftin inequality. So if I write the Haftin inequality for sub-Gaussian random variables, whose sub-Gaussian norm is like bounded by a constant, this is going to be the Haftin inequality. Okay, so there are n of them, and so there's an n here. Sort of good. If this is like not clear, just argue that because f and g are Boolean, this whole thing is going to be bounded, bounded random variable, bounded by 1 or like 2. Okay. So now here I'm going to replace t with. So this is nothing but f minus g L2pz. This is f minus g L2p. And I'm going to put epsilon over 2 here. Actually, this is squared. I'm going to epsilon over 2, epsilon over 4. I'm going to do epsilon over 4. And then, oh no. Yeah. Epsilon 2 over 4. This is going to be epsilon to the 4th times 16. And then 16 I can absorb into the constant. So this would be 2x negative c n epsilon to the 4th. Right. And so, and then I can take a union bound. So I can take a union bound says that, let me do the union bound later, but what this is saying is with probability bigger than 1 minus 2 e to the negative c n epsilon to the 4, I have norm f minus g L2pz squared minus f minus g L2p squared. This is bounded by epsilon 2 over 4. Sorry, the other way around. I'm flipping it, okay. And so in particular, it says that f, this implies that f minus g L2 Ez is bigger than or equal to f minus g L2p minus epsilon over 2 divided by 4. Right? It's just this minus is bigger than negative epsilon over 4. And so this is bigger than epsilon over epsilon squared because it's an epsilon separated set. So this would be bounded by 3 epsilon over 2 like that, which is definitely bounded by epsilon over 4. Right? 1/2 actually minus. Did I? Not 3. Yes, that was correct. Does that make sense? So this holds with high probability for a fixed pair of f and g. Now I want to say that this holds with probability, with some high probability for all f and g distinct. What can we do here? I want to upgrade this to holds for fixed f and g. Want to upgrade it to a uniform statement over f. What should I do? Yeah, so union bound, you can like imagine that this would give me probability 1 minus 2. How many pairs do we have? N squared, right? E to the negative c n epsilon to the 4. And then the same statement. So I would say f minus g L2 pz squared is bigger than or equal to epsilon 2 over 4 for all f and g in f not equal to g. And this is what we wanted to show, right? So this event, this is the event that I care, right? So this is saying over z, these are epsilon over 2 separated in the, sorry, over this event there. If this event holds, then all the pairs of functions from this are epsilon over 2 separated in this norm. The only thing that I want to make sure is that this probability is positive. If I can show this event has positive probability, it means that there exists a realization of this. So what we need to do is choose n so that the probability is positive. So I want 1 minus 2 n squared to negative c n. I want this to be positive, and how should you make it positive? So if I take n to be take n to be at least, so if n is big is good. So if n has at least like some big constant, let's say, some constant divided by epsilon over 4, and so let's do this. I want this to be small, so this is like 2e to the 2 log n, right, minus little c and epsilon over 4. I want this to be negative, right? Let's say I want like 2 log n minus c and epsilon over 4, let's say, is bigger than less than negative log n. Okay, something like that. Then I would get, let's say 100 log n, or like some constant log n. Let's see C1 or C, capital big C. Let's say A log n, A positive. Then I get 2 plus A log n is bigger than C, epsilon over 4. So n has to be bigger than epsilon negative 4, 2 plus A log n divided by C. Okay. by that. And if this is the case, then this probability is going to be this whole thing is going to be bigger than 1 minus let's say something like that. So bigger, like, which is going to be 1 minus 2 into the negative. Right, for sufficiently large n, this is going to go. So let's say take, like, n is 2, take a to be like 8. So this is going to be positive, right? But this part is easy. So this is like just verify, it make this probability go to 0 or be small. So that's the condition that we need. So that's exactly what we need. So n at least be this much. So just take it to be like the largest integer such that it's like epsilon to the negative 4, some constant log n. Okay, that's the thing that we have. Some constant times epsilon to the negative 4 log n. Does that sound good? Okay, so let's see how it is. Yeah. Yeah, so this is saying that this you need at least this much. Okay, so I can take the largest that this is. So this is saying that there exists n, right? So you can find a set which is at most this size, right? Think a little bit about this. Yeah, I can always make it bigger, but this is saying that at least I need this much. And so there exists something like that which is less than it. And if we want, it's just something like, you know, like something like that. But I can always make C bigger. Okay, just maybe quick. How can we use this to prove this lemma? Let me just try to quickly do it, maybe. So pick a finite. So we're going to prove the VC dimension covering number. So pick a finite subset of f whose functions are epsilon separated. They can always find a finite subset whose coordinate is at least as big as the covering number. So this is by the maximal packing idea, right? So maximal packing, the cardinality is bigger. So pick a maximal packing, which is an epsilon separated set of functions. I am guaranteed that the cardinality is at least this much. Then there is an endpoint set Z with cardinality less than this, such that these functions are epsilon separated in L2PZ. That's the lemma that we showed. So a very like weaker condition is like, because they're epsilon separated, the epsilon is bigger than 2. This means that when I restrict this to Z, they're going to be distinct. Because if they're not distinct, then the L2PZ norm of the 2 would be 0. Right? So this guarantees that when I restrict this G to the set Z, this produces distinct functions. And in particular, the restriction of G to Z, the cardinality is the same as G. That's the thing. So when I have a set of endpoints, such that when I restrict my function class to that, it's still like have the same cardinality. And we also know that VC dimension is, this is easy. If we restrict, the VC dimension is at most the VC dimension of the original class, which is new. Now this is a function class or an endpoint set. So we can use Sauer's law. VC dimension V, endpoint set, you get this upper bound on the cardinality. And this is by assumption, you can see that n is, I'm going to use this, plug it in here, you get that. And then there's this little inequality here that, so you can see the n here, I'm just replacing from the upper bound that I have here. And then there's this little inequality here. I can write this as C epsilon negative 4 log G divided by 2 nu, right? And this is going to be 2c epsilon negative 4 log g 1 over 2 nu. Okay, and then I'm going to bound the log g by 2c epsilon to negative 4 just by, this is a very bad bound, but the log of x is bounded by x. So that's the thing. And then I have 1 over nu here. 1 over nu. Sorry, to the nu. So this gives me 2c epsilon to negative 4 nu, and then g 1/2. Right, and then I also have, this side is also equal to g because of the fact that they're distinct. So I have g less than this, and then this gives me basically g 1/2 less than 2c epsilon negative 4. Yeah. And then I just multiply by 2, I get this, which is the result we want. So this is showing, because this is an upper bound on the covering number. And so we have an upper bound. This looks like 2c divided by epsilon to the like there's another constant c prime such that this is 8 nu, right? Something like this. So that's the result I wanted to show. Okay, it's a little tricky, but if you look at it, it makes sense. The main point is that we can restrict to a set of size n without sacrificing the cardinality of the packing. So you pick a packing, you restrict it, there's still the same number of points, so you're still bound the covering number, and then I can use the Sartre law to control, so you can get rid of the n. That's the thing. So you get rid of the n in terms of the basically epsilon, and then it's a very interesting argument. It's a little bit challenging to understand, but go through it and it makes sense. Okay. Question. Okay. Thank you, guys.